Now, so welcome everyone to this week's South American Geometry webinar. As usual, word from our sponsor. So if you want to subscribe to the mailing list, you're going to find the links on your chat. You just text or email the word webinar to us. You can also check our calendar of scheduled talks and previously recorded talks available on our YouTube channel. All the links to be found on the chat. Today, we're going to have Álvaro Ramos from Porto Alegre telling us about existence and non-existence of complete error minimizing surfaces in E-1 tall. And so, Álvaro, we're doing 50 minutes and then questions. Is that cool?
Okay, perfect.
All right, everybody, then just please bear in mind that on Google Meet, Álvaro will not be able to see you. So if you have a question, please do interrupt. We're going to agree that it is appropriate to interrupt. Or if you're too shy, you can type in your questions or comments on the chat. Okay, please, Álvaro.
Okay, thank you, Henrique. It's really a pleasure to talk in this webinar, which is, I think, one of the most important webinars in geometry, at least I've known in Brazil and South America. So I'm talking about existence and non-existence of complete error minimizing surfaces in E-1 tau. But the two words I want you to keep in mind are error minimizing surfaces and this space here, E-1 tau, which I will talk about today. So this is joint work with Patricia Klaser from Santa Maria and Ana Menezes from Princeton. And as Henrique said, please do interrupt if you have questions. I don't mind being interrupted. And let me present a short outline of the talk. I will start with some introduction, and I will put the ambient space E-1 tau in context. And then I will talk about some global results, not in E-1 tau, but in other ambient spaces about area minimizing surfaces. And then I will present our main results, which are one existence theorem and one non-existence theorem. So let's begin with the ambient space E-1 tau. And before I do that, as I said, I want to put it in context, so I will start really slowly, really from the basics, and then I will show where it stands. So our Riemann manifold is called homogeneous if for any 2 points there is an isometry of the ambient space that maps one point to the other. In other words, homogeneous manifold is somewhere you can get lost easily because everywhere looks the same. Every 2 points, they look exactly the same. The ambient space looks exactly the same from any point of view. So examples, we have the space forms, we have products, and we have any Lie group with a left invariant metric, because then you have transitive action of a group, then you can make it isometries. And you have the city of Brasilia, well, maybe not the city of Brasilia, but I do get lost in Brasilia, and I think that it looks the same everywhere, but probably it's not a homogeneous manifold. But, and you have several other examples. And let me give you examples in dimension 3, which is the main focus of my research. I love dimension 3 because I can draw pictures of it. And to simplify, I will choose M to be simply connected. So we have the space forms R3, S3, and H3. So S3 is the sphere of constant positive curvature 1. H3 is the hyperbolic space of constant negative curvature -1. And you have product spaces H2 cross R and S2 cross R. You have a bunch of many non-isometric Lie groups, and that's it. Those are the simply connected homogeneous tree manifolds of dimension 3. Of course, this many non-isometric Lie groups is a lot of homogeneous manifolds, but there is some kind of classification, and I want to present this classification now. So if you have a simply connected homogeneous tree manifold and you have isometry group iso of M, then there are 3 possibilities for this isometry group. It either has dimension 3, dimension 4, or dimension 6, and the classification goes according to the dimension of this isometry group. First, if the dimension of the isometry group is the maximal one, 6, then M has constant curvature, and hence it is isometric to R3, S3, or H3 up to homotheity, because it could be curvature 2 or curvature minus pi or whatever. So you can make a homotheity and make it isometric to the standard matrix in these spaces. So if the dimension of the isometry group is 4, this is where a lot of good things happen, and in particular, this space E minus 1 tau lies inside this bucket of 4-dimensional isometry groups. So if the isometry group of the ambient space, if the ambient space is homogeneous and you have 4-dimensional isometry group, then you can find a fibration from M into a surface of constant curvature kappa. So it's either R2, a simply connected surface. So it's either R2, H2, or S2, and it has bundle curvature tau. So here is the kappa, and here is the tau, and we call these spaces E kappa tau space. So our space is one particular example where kappa is minus 1.
Álvaro,
so
remind us what's the bundle curvature, please.
The bundle curvature is the curvature of the fibers. You have a killing field, which is perpendicular to this horizontal space, and you have the easiest way of defining it is that this bundle curvature is through the connection, the remaining connection of this killing vector. The connection between any vector x and this vertical killing field dt is always tau times this dt here. That's the easiest way of defining tau in my point of view. Cool. But so if you have this E kappa tau space, you have 5 spaces to fill the boxes, because tau equals 0 and kappa equals 0 cannot happen because this number is always different from 0. And I will present the 5 possibilities. First, if tau equals 0, then you don't have bundle curvature. Then you have a product, actually. You have just S2 cross R and H2 cross R. But if tau is non-zero, then you have some more interesting spaces that not everyone might be familiar with. First, if you have tau different from 0 and positive kappa, you have a fibration over S2, and you have a Berger sphere, which is the group SU2, which may be seen as the group of unit quaternions, but with one kind of left invariant metric. So there is a family of left invariant metrics in SU2. It's a 3-parameter family, and if this from this 3-parameter, if 2 are equal and 1 is different, then you have this metric which makes it Berger spheres. If you have all the 3 parameters equal to each other, then you actually have a round metric, and you go back to 6-dimensional isometry group, and you have S3 with a certain curvature. But if the 3 constants are different from each other, they are all pairwise different, then you don't have 4-dimensional isometry group, and this group here has a 3-dimensional isometry group, and it will show here later. So what I want you to keep in mind is that the Berger spheres are SU2 with some, but not all, left invariant metrics. Okay, so if tau is non-zero, but kappa is 0, we have nu3, which is the Heisenberg group, but not the Breaking Bad Heisenberg, I want to tell you. And it is the group of upper triangular real matrices with diagonal entrances equal to 1. So matrices like this. It has a nilpotent Lie algebra, and that's why it's called the nu group of dimension 3. And what is interesting about nu3 is that any left invariant metric in nu3 makes it an E0 tau space. You just change tau for that matter. So you don't call the Berger spheres SU2 because it's not every metric in SU2 that is a E kappa tau space, But you can call nu3 a E capital space because every metric, every left invariant metric on it has four-dimensional isometry group. And now we come to our example, which would be E minus 1 tau. So our example stands in this box. And the biggest problem about this space, it has no name. Actually, it has no name. We call it the E kappa tau space where kappa is negative. Okay, to be 100% fair, many people call this space SL2R tilde, or also PSL2R tilde. But I don't like this name, and I want to explain to you why I don't like this name and why I call it the E minus 1 tau space and not something else. So first, SL2R, that's simple, is the group of 2x2 real matrices with determinant equals to 1. And you make the quotient between this group and identity and minus identity, and you make it projective. So it's PSL2R. And this group is interesting because it can be seen as the group of Möbius transformations where AD minus BC equals 1. And why do you have to make this quotient to see this identification? Because the Möbius transformation AZ plus B divided by CZ plus D is the same as minus AZ minus B minus CZ minus D. So they are the same transformation. And there's a spider here, no longer a spider. Okay. So this group here can be seen as the group of orientation preserving isometries of H2. And here you start to see the connection between this space and H2, which is the surface where this E minus 1 tau fibers to. Okay, what else? So SL2R tilde is just the universal covering space of both these Lie groups. So it is itself a Lie group, but I am not still talking about metrics. So what are the metrics in SL2R tilde that make it an E kappa tau space? It's not every metric, and that's why I don't like to call this space the SL2R tilde, because this is a Lie group structure. SL2R tilde is just a Lie group. There is no metric in this name, and it's not every metric in this space that has four-dimensional isometry group. Actually, there are metrics in this space that make it a three-dimensional isometry group, and most metrics, to say, do that, and only this family of metrics, you have three parameters, but one is negative and the other two are positive. So if these two parameters are the same, if they are equal to each other, then you have a four-dimensional isometry group. And if they are different, you have only three-dimensional isometry group. So that's why I don't like calling the SL2R tilde, and I would like to start a campaign. Let's find a name for this poor fella, because many people get scared of it because of its name. Some people call it E minus 1 tau, other people call it PSL2R tilde. I remember the first time I've seen that notation, I got scared to hell, but later I started working on it, and it's not so bad. Okay,
Álvaro,
and yeah.
Can I stop you there? So a bunch of real quick questions. Can you just give a hint of how the relation kappa minus 4 tau square not 0, how is that derived?
I don't remember.
If not, then maybe I can pin it down. Maybe I can pin it down. So at least in the compact case, so what your table seems to suggest, that at least in the compact case, when you either on
the compact case you have S3
or a warped space, right?
Yeah, if kappa is equal to 4 tau squared, then you get an extra isometry group here in the Burgers spheres. You have some more symmetries, and then you jump to dimension 6. That's in the compact case, but in the non-compact case, I don't know.
This is necessarily a circle fibration.
Yes.
Aha. Okay, so tau really is the curvature of that guy. Right? It's the actual curvature of the circle fiber.
Yes.
Isn't it? Right. I assume the fibers are
regular,
so. Right? Yeah.
Mhm.
Okay, this is getting clear. Okay, so I can guess how one could go about trying to find this relation. Okay, tau really is the circle curvature, the circle fibers, at least in the compact case. Okay, cool. Yeah.
Thank you. This gives me time for drinking some water because I talk a lot and I need water. Okay, so one thing that I find particularly interesting about E kappa tau when kappa is negative is that when tau goes to 0, you actually see this matrix go into the product metric of H2 cross R, which is E0, E kappa negative 0 space. And in particular, this is something I found really, really interesting. H2 cross R is itself a Lie group. It has a Lie group structure, which comes from a semi-direct product. And you have a left invariant in H2 cross R, which is isometric to some left invariant in SL2R tilde, but these Lie groups are not isomorphic. The first time I've seen this, I thought, what? How can it be? You have two left invariant metrics which are isometric, but the Lie groups itself are not isomorphic, and this is really interesting. Well, fun fact. Let's put it that way. Okay, and if dimension of the isometric group of M is 3, then all you can say is that M is a Lie group with some left invariant metric, and it's not too symmetric. You don't have, basically, you don't have rotations. All your metrics are translations or reflections, basically.
Alvaro, can I add a really good
all
insight?
Your isometries.
There's a really good insight there by Jorge Lauret. Actually, he's the one who made me realize this, right? So in the context of homogeneous manifolds, right, it's not uncommon that you have, say, families of them, or even flows of manifolds which are all isometric, so they're equivalent as Riemannian manifolds, but they're quite different as homogeneous manifolds in terms of the underlying algebraic structure. So for guys who work with these things, this is not surprising, but it was surprising to me, right? I mean, once you see it, then it's no longer surprising. But he says it's quite a common feature. So you could have, for example, a geometric flow which is isometric, but at the limit, there's a transition in the algebraic structure. Some action changes, right? So you're still isometric, but as a homogeneous manifold, you're inequivalent.
You are totally. This is
to the point.
That's quite fun. Yeah, that's interesting, and that's surprising to me too. But as Lie groups, you already are not equivalent. So let me go a little faster because I'm still in the introduction. And just remark, we will set kappa equals to -1 because it's just a homothety, and we don't care much about it. And the specific model we work with is the cylinder model, and here is the metric. And you can see that when tau is equal to 0, this term disappears, and you have only a product metric, which is exactly the metric of H2 cross R in the cylinder model. Lambda is the conformal factor for H2. Okay. Now let me give a few words about global results on area minimizing surfaces. First, a definition: what is an area minimizing surface? First, a compact surface is area minimizing if it has the least area among all other surfaces with the same boundary. And a complete surface in a Riemannian manifold is area minimizing if any compact subdomain is itself area minimizing in this sense. So some facts about area minimizing surface: if sigma is area minimizing, then it is a minimal surface. That's a no-brainer. And the other way around almost happens. If sigma is a minimal surface and you have a point, then you are locally area minimizing. So small parts of minimal surfaces are area minimizing compact surfaces. And finally, this is the most important fact that I will use today, is that if sigma is area minimizing, then it has to be smooth and properly embedded. The idea for that is that if you are not smooth, then you have a corner. And if you have a corner, you can lower the area a tiny bit, so you are not area minimizing. The same thing goes for embedded. If you're not embedded, if you cross yourself, then you can make kind of a hole in it, and you can make the area locally a little smaller. And also, proper is, you can obtain properness. If you accumulate, then you have curvature estimates. It will be graphical over yourself, basically in some parts of your manifold, and then you can replace two disks by a little tube to decrease area. So if you are area minimizing, you are the nicest kind of manifold of surface you can be. So some examples of global results about area minimizing surfaces. In R3, you have planes, and that's it. You only have planes as complete area minimizing surfaces in R3. In S3, you don't have nothing at all. There are no complete, in this case, closed area minimizing surfaces in S3. You can always decrease area. Actually, you don't have stable minimal surfaces in S3. And in H3, the situation changes completely. There's like a lot of area minimizing surfaces. They are all different from each other. And this can be seen by this theorem by Michael Anderson, 1982. I think it was published in Invenciones. And it states something like this. If you have a smooth curve in the asymptotic boundary of H3, which I will define in the next slide, so there exists an area minimizing surface with that particular asymptotic boundary. So this is called the asymptotic Plateaus problem. Plateaus problem, you have a curve in a manifold, and you can find an area minimizing surface with that boundary. So here you have the same problem, but asymptotically. Just a remark, along the talk curve, I mean a finite collection of pairwise disjoint simple closed curves, and they will be usually piecewise smooth unless otherwise stated. So let me define what is the asymptotic boundary of H3 and say a few more words about this theorem. So first we take the ball model for H3, which is the unit open ball with this metric, a conformal metric to the Euclidean metric. And you can make the compactification of this space by compactifying this ball with a certain topology, which is called the cone topology. I will not go into details, but there is a topology that makes this a topological space, and this topology has some relation with the geometry, the intrinsic geometry of H3. And we let the asymptotic boundary of H3 to be the boundary of this topological space. Since you have topology, you have convergence, you can make limits. And if you have a surface in H3 or any subdomain for that matter, you can define the asymptotic boundary of sigma as the limit points at infinity. So there is a sequence in the finite part of sigma that converge to this point on the boundary of this ball. So the figure is exactly this one. Here is the asymptotic boundary of H3, is the boundary of this ball. And the theorem of Anderson says that you have a curve, so you can have more than one component, but every component is a simple closed curve and smooth. So if you choose any curve, you can find a minimal surface inside of H3, which has this curve as asymptotic boundary. This picture here is misleading because in this situation, probably it would be disconnected, it wouldn't be connected, but we don't care. Actually, he proved this using heavy arguments on geometric measure theory, which nowadays are more standard, more classic, and we can do things in a more geometric manner, in my opinion. I'm not an expert, far from that, on geometric measure theory. So in H2 cross R, which is another very important space for us, we consider the cylinder model. So we have H2, which is the disk, and we make it cross R. So we have H2 cross R. And the asymptotic boundary we will work with, it's not the asymptotic boundary of H2 cross R, but the asymptotic boundary of H2, which is this circle, cross R. So it is a cylinder. It is an infinite cylinder, the asymptotic boundary. We don't work with the compactification of H2 cross R. And this is abuse of notation. We call it the asymptotic boundary of H2 cross R, because we don't like parentheses, basically. So as I said, there is an intrinsic notion of the boundary of H2 cross R, but it does not admit a differentiable structure. It looks a little like this lime-like surface. It has two singularities, and I won't say anything about this kind of space, but it is useful in certain situations. So first theorem about global results on area minimizing surfaces in H2 cross R. I will present this one by Nelly and Rosenberg in 2002, which states if gamma is a graph over the asymptotic boundary of H2 cross 0, then you can find an entire minimal graph in H2 cross R with that asymptotic boundary. And since it is entire minimal graph, it is area minimizing. So you can find area minimizing surfaces in H2 cross R. From this result, you know that you have many. For any graph you choose here on the asymptotic boundary, you have an area minimizing surface with that asymptotic boundary. So this is called the asymptotic Dirichlet problem. So you also have non-existence results by Sarup and Tubiana, which says that if you have a curve that contains a thin tail, and a thin tail, it's this little part of the curve. Here you have another thin tail, and precisely a thin tail is a part of the curve which stays in one side of a vertical segment, so it has this maximum or minimum on the angle function, but it is also thin. It cannot go very far on this asymptotic boundary. The height has to be less than pi of this curve here. So this is a thin tail. If the curve contains a thin tail, like this curve here, for example, then you don't have any minimal surface in H2 cross R with that asymptotic boundary. So this is a non-existence, stronger non-existence theorem, because it states that there is no minimal surface. If there is no minimal surface, there is also no area minimizing surface. Okay, so on one hand you have existence if gamma is a graph.
Clarify one thing? Can I just clarify that I have no responsibility over this horror? This is my cousin Ricardo.
Oh yes, you're right. Sorry, Enrique, I totally forgot. Yeah, it's not me. It's not Enrique. You're right. Yeah. Okay, thank you. So I had forgotten about that. Sorry. Okay. So in one hand you have existence if gamma is a graph, and in the other hand you have non-existence if gamma has a thin tail, which is basically a maximum point for the angle function. So what is in between? How can you not be a graph and not have a thin tail? You would have to have some kind of fat tail, which would be this vertical segment. On every point, you attain a maximum or a minimum for the angle function. So the curves would look a little like this curve in here. And this is called the asymptotic plateau problem, because these are the curves we still don't know if they exist or if they don't exist. And before I give you the main theorem in H2 cross R for this kind of curves, I need some definitions. So take a curve in H2 cross R, in the boundary of H2 cross R, and you take any point here on this boundary of H2 cross 0, and you consider this vertical line over this point. So this vertical line might intersect or it might not intersect the curve gamma, but if it does, you consider the connected components of this vertical line minus gamma, and you can look at the height of each of these components, and the height of gamma at the point P is going to be the minimum height, the minimal length of this little pieces. So in this picture, this piece has the least length, and length here, I mean Euclidean length. So it could be infinite, this minimum. If it is a graph, the height at all points is plus infinity, and if you don't intersect the curve, it's also plus infinity, and etc. So, and the height of gamma is the infimum of all these heights, pointwise heights. So in this picture, this will be the height of gamma, this distance here. And usually it's not an infimum, usually it's a minimum. In this picture, it is a minimum, but we define it as an infimum. Okay, so the theorem about error minimizing surfaces in H2 cross R would go to Barry's Koski-User in 2014. If you have a curve in the asymptotic boundary of H2 cross R, which is tall in the sense that the height at every point is bigger than pi, this is a tall curve, then you can solve the asymptotic Plateau problem. There exists an error minimizing surface there with that asymptotic boundary. On the other hand, if you don't have this, you have an open arc such that the opposite inequality, and it's less than pi for all points in this interval, then you don't exist. There is no error minimizing surface with that asymptotic boundary. So some remarks, actually the statement of this theorem is a little different, but it is basically equivalent to the one I am presenting here today. And if the height of the curve is exactly equal to pi, so if you have points with more than pi, but you kind of get close to pi, the problem is still open in some sense. Open in some sense because there are examples both for existence of area minimizing surfaces and for non-existence of area minimizing surfaces. But there is still a lack of classification, which are exactly the curves with height pi where you have, and which are the curves that you don't have area minimizing surfaces. So something to think about. And I am not mentioning other results on area minimizing surfaces in H2 cross R, but they can be found in the work of Fleckner and Mazzeo in 2017, Ferrer, Martin, Mazzeo, and Rodriguez in 2019, and this year recently another work of Koski-User in 2020, which is a little more general than this one. Okay, so finally, I can go to our results, the main results we present here. They are actually motivated by this theorem here of Koski-User. So that's why I presented this with a little more care and gave all the definitions, because everything is going to be more or less the same. We, again, use the cylinder model for E-1 tau. So it looks like the pictures will look like the pictures for H2 cross R. And we consider the asymptotic boundary of this manifold just the same way we did as H2 cross R. We consider the boundary of the disk times R. So it's S1 cross R. And again, the definitions of height of a curve at a point and the global height of a curve are the same. You take this vertical segment and you consider the Euclidean length of the connected component, and you take the minimal number. So the first result I want to present today is the existence theorem, and it goes like this. You take a curve in the asymptotic boundary of E-1 tau, and if the height of this curve at every point is high, in the sense that it's larger than the square root of 1 plus 4 tau squared times pi, so we call this a tau curve, then you can find an area minimizing surface sigma with that asymptotic boundary. So again, you can find a lot of minimal area minimizing surfaces in E-1 tau. And on the other hand, we also have a non-existence theorem, but unfortunately, the bound is not the same. We didn't find the same constant here. If there is an open arc such that the height is less than the square root of 1 plus 4 tau squared, and here is a term which we don't like, minus 4 times the absolute value of tau times pi, then there is no area minimizing surface with that particular boundary. So some remarks. When tau is 0, these are the same bounds as the work of Koski-User, and the results are equivalent. But if tau is large, if tau is larger than 1 divided by square root of 12, which is, it looks a little arbitrary, the non-existence theorem does not apply. This theorem here makes a constant to be negative, so you cannot have a positive number less than a negative number. So unfortunately, we don't cover all values of tau in the non-existence theorem. But recently, Jesus Castro Infantes, which is a student of Magdalena Rodriguez in Granada, he used a distant technique to improve this constant, and the same result holds, substituting this value here by 2 times the square root of 1 plus 4 tau squared. If these two were pi, we would be like in the best shape, but it's 2. So we still think this is not the sharp constant. And again, there is room for improvement here. Or maybe you can prove that this is the sharp constant, so another open problem. And to me, this is a little tricky. I don't know how I would improve this constant here. But okay, so another result about error minimizing surfaces in E-1 tau is by Folha and Peñafiel, where they kind of prove the same result as Nelly and Rosenberg. When gamma is a graph over S1 times 0, then you can find an entire minimal graph with that asymptotic boundary, and if it is an entire minimal graph, it is error minimizing. Okay, so let me prove you, or at least give you an idea of the proof for the existence theorem. So here's the statement again, and let me explain the main steps in the proof. First, we prove the result when gamma is a family of parallel circles, horizontal parallel circles, and then we go for the general proof separately. And I think this is fun because you first prove this very specific case, and then you prove the general case using that is not this very specific case. I like this aspect of the proof, but okay. So then you go for the general case, and here the proof is more standard. You find a sequence of curves, gamma n, in mean convex compact domains inside of the ambient space, such that these curves, when n goes to infinity, they kind of converge in this topology of the semi-compactification, they converge to gamma. And then you solve Plateau's problem for this curve gamma n, and you find a compact error minimizing surface. This domain here, delta n, is mean convex. So the surface stays in this domain delta n, and the boundary of this curve, of this surface, is gamma n. And here is boundary, is real boundary, because everything here is compact. After that, you have to show that this sequence you found converges to something which is an error minimizing surface of E-1 tau, and then you show that actually the asymptotic boundary of this surface you found is what you wanted. So these are the main steps. It is kind of the traditional steps when you prove theorems like that. So let me explain to you why the theorem holds when gamma is a family of parallel circles. So you take this family of parallel circles where any two circles are far apart, are farther than this constant here, which is the constant on the statement of the theorem, and I'm thinking that they are ordered. So C1 is the lowest, C2 is the second lowest, and so on and so forth. And then you just say, my error minimizing surface is gonna be this family of parallel planes. Each individual parallel plane is an error minimizing surface, but it could be that the union of them is not an error minimizing surface. So to prove that it is actually an error minimizing surface, you need to use the hypothesis that these disks are far apart. So we prove that, oh yeah, sure, I already said that. So we prove that there is no minimal surface inside of E-1 tau, which is connected and has boundary components up in this plane and down in this plane. And this proves that these two planes together are area minimizing, because if there is no surface like that, then any domain you choose here is going to be the minimal surface is going to be disconnected and inside this family of planes. So let me show you how we prove this. It's simple. We just use a family of rotational catenoids, which was obtained by Carlos Peñafiel in 2012. These rotational catenoids, they are complete minimal surfaces. They are not error minimizing. And they look like that. When they are very high, when these two circles, these two boundary circles are far apart, then this catenoid is almost going to infinity. And the largest height for which they exist is exactly this number. Actually, they exist for any difference on height less than this number. And so you start very high, and so they escape from the compact surface here you are assuming exists, and now you start to make them closer together until you have a first point of contact, which is guaranteed by the fact that when these two circles go to zero, the distance between these two circles go to zero, they converge to a horizontal plane with multiplicity 2. So there is a first point of contact, and you have two minimal surfaces, one on the other side of the other. It's a contradiction with the maximum principle. So this surface doesn't exist, and this is going to be the error minimizing surface with this asymptotic boundary. Okay, so this proves the case in the very specific case, and now we go for the general case. So let gamma be a curve as stated, and first I will build these domains, delta n. We take this exhausting sequence of disks in D cross 0 by concentric disks, all centered at the origin, and for this is amazing, but we actually need to use the origin. For some reason, which I will explain really later, it's important to have the center of these disks on the origin. So we take this sequence of disks, which exhaust the disk D times 0, and you make these cylinders. This would be solid cylinders, dn times minus t, where t is large enough so that gamma is contained in this open product neighborhood. Okay, so delta n is mean convex by simple reasons, and we can use the coordinate systems of this cylinder to project. We horizontally project gamma into each of these compact cylinders here, and you find a curve gamma n in the boundary of delta n. There's a misprint here. Okay, so then we solve Plateau's problem, and you find an area minimizing surface in that domain with that particular boundary. And we know that the number of connected components of this surface is uniformly bounded by the number of connected components of gamma, which is finite. So we may pass to a subsequence to assume that the number of connected components of sigma n is constant. And by simplicity here in the talk, I will think that this number is 1. Or in other words, we will assume that sigma n is connected, although gamma could be disconnected. Okay, and now the proof begins. Here is just setting up the things, and now we begin the proof. So let omega be the complement of gamma in the asymptotic boundary of your ambient space, and for any point which is in this omega domain, which means for any point which is not in gamma, we can separate this point from gamma using a very, very nice surface, which is called a tall rectangle. So a tall rectangle was obtained first in tau equals 0 case by not Henrique, but Ricardo Sayert and Eric Tubiana in 2008 in H2 cross R, and extended for our setting by Folha and Peñafiel in 2014. And the idea for the tall rectangle is this: you take any angle here less than pi that you want, and you take any height which is larger than this number that you want. So there is a complete area minimizing plane in E minus 1 tau. It is invariant under a one parameter group of hyperbolic isometries, and it has this kind of asymptotic boundary. So I'm not sure if you can understand this picture, but here will be some height, and this point is a little above. But if tau is equal to 0, this would be a horizontal segment. So it's a little tilted rectangle. That's why we call this a rectangle, a tall rectangle. And this is just the asymptotic boundary of a tall rectangle. The tall rectangle is a surface inside E minus 1 tall. Okay, so let's use these tall rectangles as barriers. Take gamma curve as before, so any 2 points in the same vertical line on the ambient space, on the asymptotic boundary, are far apart, and you take any point which is not in gamma, and you take this tall rectangle. It could be thin. It's a thin tall rectangle which separates this point from gamma. So I will go a little faster now, if you don't mind. So this tall rectangle separates the ambient space into 2 regions, and this point P is one of the regions, and gamma is the asymptotic boundary of the other region, basically. So since the boundaries of sigma n is converging to gamma, the boundaries of sigma n is contained in this other region, which is not in P. So the thing is, since both these surfaces are area minimizing and the boundaries don't intersect, then the surfaces cannot intersect. So this tall rectangle acts as a barrier so that your sequence of surfaces stay away from this point at infinity for any point that you want. So this argument shows that if sigma n converges to something, then the asymptotic boundary of this something must be contained in gamma, because any point that is not in gamma can be separated by the sequence of surfaces sigma n. And now we use this separation property to prove that sigma n converges and that the asymptotic boundary of sigma is actually gamma. So let's prove that it has a convergent subsequence. First, and here's funny, since it's not a family of parallel circles, that's how it starts, there is a horizontal plane such that the boundary of this horizontal plane intersects gamma transversely. And now, what do? I will skip some things here and I will go directly to this picture. Here is the point where the horizontal plane intersects gamma transversely, and you choose 2 points here such that this arc only intersects your big curve gamma in 1 point. You can gamma has to intersect elsewhere, but locally it only intersects in this point because it's a transverse intersection, so you can find this arc here. And then you complete this arc with another arc on P, on this horizontal plane P, and you consider this region here. And now you have curves gamma n which are converging to gamma. So eventually, for n sufficiently large, gamma n will intersect this disk A only 1 time, and the intersection is going to be transverse. So the linking number between this closed curve here, which is the boundary of a disk, in the product manifold, the closed disk, of course, R, between this closed curve here and the curve gamma n is 1. Since this is a linking number property is a topological property, and this is the boundary of a disk, and gamma n is the boundary of another surface, there will be another point of intersection between the boundary of A and the interior of sigma n. So there is this point Qn. Now, since P1 and P2 are not in gamma, we can separate them from sigma n using tall rectangles. And what's left here, it's a compact arc. So for any n, you have a point in this compact arc, which is compact, I already said that. So you have a convergent subsequence of a point. So you have a sequence of points Qn, each Qn in sigma n, and these points Qn converge to something, to some point. And then this is a standard argument. So sigma n has to converge to a complete area minimizing surface sigma, which passes through Q. Okay, now we need to prove that the asymptotic boundary of sigma is actually gamma, and what's missing is to prove that it is contained in gamma, because we already know that gamma has to be, that the other way around. So we still need to prove that gamma is contained in the asymptotic boundary of sigma. So again, start with the same picture as before, assume that gamma is transverse, and you take the same sequence of points, and you have this point Q. And Q is in sigma intersection with gamma. But now you can make these 2 points smaller, and you can repeat the argument for a sequence of points. And you find for each arc here, you find another point. And all these points are going to be in sigma. So if all these points are in sigma, and by construction, these points are converging to P, then P is in the asymptotic boundary of sigma, and you prove that this point is in the asymptotic boundary of sigma. But this is when P is transverse to horizontal plane, but this argument is just topological. So we can use a point where is not transverse to P, we can use an analogous argument, changing P to a vertical plane, and this proves the existence theorem. So in the last 5 minutes, I will go really fast. I want to give you an idea of the non-existence theorem, and more importantly, I want to give you an idea why we have this -4 times the absolute value of tau here. So outline of the proof is simple. We take a gamma as stated, and this number, which is half of this height, so we can think that above is H0 and below is minus H0. And we construct this minimal surface. We assume that there is a minimal surface here, and we go to a sub-arc such that any 2 points in this sub-arc are less than H0 plus minus epsilon distant apart. Actually, H0, 2H0 minus 2 epsilon apart. Particularly separates E minus 1 tau into 2 disjoint regions.
Sorry, can everybody hear Álvaro? I think I lost him.
I can't see him.
Can you or can you not?
No, I cannot.
Álvaro, if you're there, give us a sign.
I think he's out of connection.
Is it down?
Yes.
Can somebody what's him up?
Can somebody finish the proof?
I think he's about to log in again. But
Álvaro is still there?
no, he dropped. And he may not have realized it. So.
Are you suggesting he's still speaking by himself?
I am, because you can't see it. That I honestly think that's what's happening. Yeah. Let's see what happens. I'm contacting him in a parallel here. Is Petruccio here? He is. Can you send him a WhatsApp message, because
Okay, yes, I already sent a message to Álvaro by WhatsApp. Let's wait.
Yeah, thanks. I don't have his WhatsApp. We were talking by email. Maybe I'll write to my cousin and ask him to finish the proof or something.
Maybe he won't see the message because he's still presenting.
Yeah. I don't know how to address this. This is the first time it happened.
Maybe Max will call him.
Yeah. Maybe we should have a backup entertainment, somebody to come in and just do something.
Do some Aikido aí, mano.
Well, Patricia Klaser is here. Maybe
Excellent.
Finish to talk. I'm joking.
Maybe we can take some questions. I actually half mean this, so maybe if Klaser wants to take the questions, if he isn't able to come in, that would be good.
I'll try to call with Álvaro.
Yeah.
Você consegue voltar? Estamos aqui esperando você. Você caiu, você caiu. I guess just written, yes.
Okay. Is he coming back? Well, why don't I then just use this free time to remind you that next week we're going to be meeting on Friday. We're going to have Asun Jimenez from UFI. So book it down. Álvaro.
Yeah,
There he goes.
I don't know what happened. Which was the last slide you've seen?
Did you finish the talk on your own?
Where have you been?
I think the battery of my earbuds went off, so we turned off everything.
Okay.
What's the last slide you've seen?
Let's have a look.
Okay.
And maybe just let's strategize a bit because we skipped 10 minutes on this. So maybe you can wrap up sort of to the final punchline and your final remarks, and then we can take some questions.
Let me ask you this. Have you seen the whole existence theorem?
We're about to see the converse, where the gamma is in the boundary and the boundary is in gamma, right? So we're about to see the converse.
Oh, okay. So you haven't seen that. Oh, it's been a while.
Yeah. Maybe we have to agree to leave this to the paper, and then you can make a final remarks.
Of course, the converse is more or less like this. Okay.
Yeah. Okay.
You start thinking that you are transverse again to the horizontal circle here, and if you are transverse, you find this point for any arc you choose that you intersect once.
We're not seeing your slide.
You have to share your screen.
Oh, sorry. I hate this. Okay, where do I do that? Okay, sorry. Really sorry.
Hand waving.
Okay, now you can see my slides.
Yes.
Okay, so first as I said, first we think that P is a point in gamma, and we want to show that this point is also in the asymptotic boundary of sigma. If P is a point where the horizontal plane is transverse to P, you just make the same argument as before, and you can find Q, which is in the intersection of sigma and gamma, in this compact part of this arc, and this point is in sigma. Now this can be done for any arc you choose. So you get a smaller arc, you get another point in sigma. And if you get a smaller arc, you get another point. And eventually, you get a sequence that converges to P by construction. So this point is in the asymptotic boundary of sigma. Remember, you are not making the convergence of sigma n again. You are just working on sigma. And then, if you are not transverse to this horizontal plane, everything I said is just topological. So you can just change a horizontal plane to a vertical plane instead, and you again find that this point is in the asymptotic boundary of sigma. So that's for the existence theorem. And the non-existence theorem, I can wrap it up in one picture, which is the most important one. This picture here. So assume you are really not tall, you are a short curve. So you have a curve here which stays between this height and this height, at least for a segment on the asymptotic boundary. And we have some space here, you have a minus epsilon. So what do? You first construct this product neighborhood V, which is separated at least twice by sigma. If you have this product region here, you know that sigma is properly embedded, so it's orientable, and it separates the ambient space. So the top of this neighborhood here is in one of these two regions. The bottom of this neighborhood is again in the same region, but in between, it changes to the second region. Sigma could enter here again, but we don't care. We just care that there are portions of this neighborhood which are in this other part of the ambient space. Now, we start with an area minimizing surface, which we can find, which has boundary up here, really high, up, and then we translate this surface here so that the projection stays inside the projection of V. We use some parabolic translations to do that. And then, since we can do this, we don't know where the boundary goes, because this is the main difficulty. When you have an isometry of H2 cross R, it comes from an isometry of H2, and the height function is preserved. But this is no longer true in E-1 tau. So you need to have control where this boundary goes, because it's up here when you are in the original area minimizing surface, but when you translate, it changes the height. And actually, we can see that you can change mostly by this number, 2 times the absolute value of tau. So when you translate from up here to down here, you stay away from this neighborhood here, V. So now you intersect, you have an area minimizing surface, compact with boundary, area minimizing surface F of S1, which intersects sigma at least twice. And now you can forget about this neighborhood V, and you have 2 area minimizing surfaces intersecting. And the thing is, you can exchange a portion of this surface here for a portion of sigma, both compacts and with the same boundary, to obtain a non-smooth area minimizing surface in E-1 tau. And that's the punchline, that's the contradiction, which shows that sigma cannot exist in area minimizing surface with this part of gamma as asymptotic boundary. And this is why we need to add this -4 times tau in the statement of the theorem, unfortunately, because we need control on the height of the boundary of this minimal surface. If it was higher up, this boundary would intersect, and then you cannot replace correctly. So yeah, that was it. Thank you. Sorry for...
All right. Thank you, Álvaro. Okay, so in the hope that the Panda finished up well, do we have any questions for Álvaro? Any specific
So,
question?
Álvaro, you have existence above some height, non-existence below some other height. How can the transition go from non-existence to existence, or the other way around?
Yeah, I would love to know that. We expect that the same bound for the existence should be the bound for the non-existence. The problem is that we don't have a proof for that because of this huge difficulty on the isometry group of E minus 1 tau. Everything changes height because, and it changes like a lot. And the picture that I showed to you, the last picture, it's actually accurate. It's not just that this in this slab actually start sliding and changing the height, so you become almost vertical and you achieve that distance. So the way that Jesus did to improve a little bit our constant was to go to another model of E minus 1 tau, which would be the half space model. And there the isometries behave a little better, so he could improve our constant, but still didn't find a sharp constant. And actually, my guess would be that the sharp constant would be the square root of 1 plus 4 tau squared times pi, and that's it. But we actually don't know how to prove it, or we actually don't have a strategy for that.
And yeah, but even if it's the same constant, so below that constant non-existence and above existence, what happens, like, what kind of transition would you have? Like, suppose you take a minimal surfaces that go down until, so they exist until one height, and then what happens? Where do they go? Like,
they go to infinity. They disappear. They start to exit any compact. Like this family of catenoids. You have this family of catenoids always bounded between, let's go to H2 cross R, because that's what happened in H2 cross R, and we know that happens in H2 cross R.
oh, there is a maximum height.
The maximum height, they start going, getting fatter and fatter until they just disappear, they vanish. And if you go from,
maybe they go to the boundary. Maybe they go to the boundary.
and if you go from above to below, what happens is like this. You start getting closer, 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 and you disconnected actually. And when you get that height, you have something which is least area, which will be this catenoid here, and you could decrease area in this very large domain close to infinity, and that starts getting smaller when you go down, like this planes. This is the picture I have in mind.
Thank you.
Sure, thank you.
Very interesting.
All right. Have you got any further questions, Flavo? In that case, thank you all, and Álvaro Krüger for bearing together despite of the technical problems. And
I'm sorry about that.
Let's thank him again, please. Yeah.
Thank you, Álvaro.